welcome guys. Hi Mansetters. I hope you had an awesome 2 minutes break if you've been watching the grade 11 show and maybe you're interested in doing the grade 12 show and prepare for the next coming year. And for the grade 12s, I hope you're watching this show because it's very, very important. And helping us for the next coming hour, it's the beautiful Natasha.
Thank you, Sepo. Okay, guys, just grade 11s, just a little provisor over what Sepo said. Please don't tune in. Calculus, you will not be touching at all in grade 11, so don't even bother about it. It doesn't really relate to anything else that you do in grade 11. So, well, it does. It relates to everything, but I think it can be a little bit confusing for grade 11s. So grade 12s only.
Yes. So, guys, don't crack your brain. Just have a break, do your homeworks or something like that. But grade 12s, stay right where you are. Please, Natasha, take the board.
All right, thank you.
Okay, guys, while you're on that, remember to go to our Facebook page, like our page. Or if you've been on our page before, you know how we do this. Simply ask any question, any query that you have. We are here to do it with you. It's facebook.com/LearnExtra. Or visit our funky website. It's learnextra.co.za/live, and we also on Twitter. Yeah, it's @LearnExtra. Simple as that. Now, with no waste of time, Natasha, please take over.
All right, thank you, Sepo. All right, guys, so today, as I said, we're looking at calculus. So calculus really brings everything together in maths, as you will see as we go on with the lesson. A lot of things that you learned in grade 11 that were kind of long, you can do them in a quick way in grade 12. So it's a nice, exciting, cool section for grade 12s to do. So in today's lesson, we're going to look at limits, and we're also going to calculate the derivative from first principles and the derivative by rules. Okay, but before we get to any of that, I just want to look at what calculus really is. So, you know, every now and then, well, actually every single time we do a new section, people will say, but why are we learning this? Well, calculus is really one of those big important sections in maths, and I swear to you, none of the other sciences would exist without calculus. So what is calculus? Calculus is the study of rates of change, okay? So we often call it the study of motion. And so it's the study of rates of change and motion. And as I said, it's one of the most powerful mathematical tools ever invented and really makes everything work. It's used every day by mathematicians, physicists, engineers, and indirectly by a whole number of other professions, okay? Getting into the nitty-gritty of stuff, calculus is divided into two parts. You get differential calculus, which is what we're going to look at today. Differential calculus deals with the rates of change and the motion and all of that. The other part of calculus is called integral calculus. Now, integral calculus deals with areas and integration. That's not something you do in the normal grade 12 syllabus. Integration, you will do it if you're doing AP Maths, and you will do it if you go on to study maths in later years in your commerce degree or pure maths or whatever the case is, but integration is not for the pure maths grade 12 syllabus. Okay, so you don't have to worry about that. We'll only be looking at differential calculus. As I said, there's lots and lots of real-life applications of calculus, and I'm just going to go through one or two of them, but really you can read this from your notes on the website. Okay, one of the people that use calculus a lot are biologists, and they use calculus to determine the exact rate of growth. Remember I was saying we're talking about rates of change, motion, things are changing. So biologists would use it to find the exact rate of growth in a bacterial culture when different variables, okay, such as temperature and food source are changed. Okay, as soon as you see the word changes, you've got to start thinking calculus, okay? The research helps them increase the rate of growth of necessary bacteria, which is very important, or it will decrease the rate of growth for harmful and potentially threatening bacteria. One of the other uses is an architect will use integration to determine the amount of materials needed to construct a curved dome. Think here of the Moses Mabhida Stadium in Durban. And as well as calculate the weight of the dome and determine the type of support structure that's required. And then something that you wouldn't think you really use calculus in, well, it's used indirectly by graphics artists. Okay, so people think, okay, I'm going to go into an art subject, I'm going to get away from maths. Not going to happen. Uses calculus, a graphic artist uses calculus to determine how different three-dimensional models will behave when subjected to rapidly changing conditions. This can create a realistic environment, especially when you're talking about movies and video games and that kind of thing. So graphic artists, if you were going to do it and you thought there's no maths, there is a little bit of maths, but don't get too scared. It's nothing hectic. Very, very simple kind of maths you'll be using. Okay, and as I said, one of the things we're going to discuss today is the concept of a limit. So let's get straight into the lesson. All right. Now, you might have heard of limits. What is a limit? When we find the limit of a function, we look at what happens to the function value, so what happens to the y values as we get closer and closer to a specific x value on the curve. The best way for me to explain this is with an example. So I'm going to go straight into the first example. I'm just going to explain to you some of the notation. The question says find the limit as x approaches 0. We read that arrow as approaches. Okay, so as x gets closer, in this case, to 0. Okay, so find the limit as x approaches 0 of the function 3x plus 6. So first, let me just draw a graph and show you what's happening. Okay. And we've got a straight line graph. 3x plus 6 is a straight line. So this is f of x is equal to 3x plus 6. And the y-intercept of this graph is 6. Okay, so when we're asking you to find the limit as x approaches 0 of the function 3x plus 6, we're asking you to see what happens to the y values as x gets closer and closer to 0, both from the right-hand side and from the left-hand side. Okay, so what happens to the function, the values of y, as x approaches 0 from the left and as x approaches 0 from the right? Now you can see from the graph that I've drawn that the function value will be 6 when x is equal to 0. So as x approaches 0, the function should approach 6, right? So how do we set this up? So we write the limit as x approaches 0 of 3x plus 6. And all you simply do for the x approaches 0 is you substitute x is equal to 0 in place of x. All right, and you're going to get 3 times 0 is 0, 0 plus 6 is 6. Okay, so therefore the limit as x approaches 0 of the function 3x plus 6 is equal to 6. Okay, and remember what that's telling us is that as the values of x get closer and closer to 0, the y values get closer and closer to 6. Okay, so if you were to actually take values for x and substitute it into the function value 3x plus 6, you will see as you get closer and closer to 0, so if you took negative 0, 2 and then positive 0, 3, and you took values really, really close to 0, you would see that your graph would get closer and closer to 6. Now, for grade 12 purposes, you don't really use limits much when you're drawing graphs. But as you draw higher order graphs, which you guys I know won't be exposed to, but I just want to give you an idea of when we're going to use this whole concept of a limit. When you draw x to the power 4 graphs and that, when you go to varsity level, you'll see that limits become really, really important because you can't tell what's going to happen to a graph unless you use this concept of a limit. Okay, so it's a very, very important concept in calculus. I think what we should do, I'm going to cross over to Sepa to see how you guys are doing, but we can either take a break or carry on with the next example. What do you think?
Okay, we can carry on with the next example. We still have time.
All right. Okay, guys, so I'm going to take another example and I'm quickly going to make one up just to continue with this idea of a limit. Find the limit, and I'm going to say of x as x approaches 2 of the function x squared plus 2. Okay, so we want to find the limits as x approaches 2 of the function x squared plus 2. So if you were to draw it to get an idea of what's happening, this is obviously a parabola, a very basic parabola turning at 2 on the y-axis. Okay, and what we're saying is, well, what's going to happen as x approaches 2? So let's just say that this is the value of 2 here. Okay, so we want to know what's happening at this point on the graph when x is approaching 2 from the left-hand side and when x is approaching 2 from the right-hand side. So what does the function value tend to? Okay, so all you do is we say limit as x approaches 2 of x squared plus 2 is equal to, and you're simply going to substitute the x is approaching 2, you substitute x is equal to 2 in place of x squared. So this is going to become 2 squared plus 2. So it's going to give me an answer. 2 squared is 4, 4 plus 2 is 6. It's going to give me an answer of 6. So if I didn't know what that value is on my graph, we can work it out using limits that the function value will be 6. Okay. Also very important is when you set up your limits, please make sure that once you've got your answer, you don't have limits still hanging around in your answer and that. You don't want any of that. You want a limit just in the question and then your answer just on the other side. So you don't want to have limits once again in the answer on the right hand side. Okay, it's important that you understand conceptually what you're doing, and if you're putting the limits on the right hand side after you found the answer, it doesn't make sense. Okay. All right, so I think now we should go to a break before I cross over to the next section.
Yes, we can go to a quick ad break, but I have to say something. Nsovu Macau says hi to you, Pastor.
Thank you so much. Hello.
Seems like the guys are enjoying the show.
Brilliant.
Okay, guys, I like the way you enjoying the show. Grade 12s. I know the energy is so packed. Almost half a year. Time really flies when you are just looking back, guys. I hope that you are taking all the notes, you understand, and our notes, you can find them on our website. It's learnextra.co.za/live. But for now, guys, you'd have to forgive us because they are not yet there. You can still catch them tomorrow. You can get them tomorrow and paste them on your bedroom walls and such things like that. So let's take a quick ad break and grab a glass of water. See you after this. Welcome back, guys. I hope you had an awesome ad break right there. I hope you had a glass of water and looked at your notes and prepared those questions. I'm waiting for those questions here, but I don't see any question. Maybe you understand or what, I don't know. But for now, I hope you're sipping on that key concept for calculus because you have to get the key concepts before applying. But now, with no waste of time, let's give it back to Natasha. Natasha.
All right, guys, I hope you've had a good break. As Sepu said, I hope that you get those questions coming in. Now, I know for some of you, you might have just started this section. So if you get a little bit lost, you will get there by the end of the week, I'm sure. Calculus is such a big section. Teachers can't afford to waste too long, not doing certain parts of it. So make sure you understand this. Give yourself a good grounding so that when you do it in school, you understand perfectly. Okay, but I know some of you are already flying ahead with first principles and that kind of thing, which we will get to. So what we're going to look at now is the gradient of a curve at a point, and we're also going to look at finding the gradient from first principles. So just to go over the gradient of a curve at a point. Now some of you guys would have done this in grade 11 last year. To find the gradient of a curve between 2 points, so we're not talking about 1 point, but if I've got a curve, and again I'm going to stick to the easy parabola, and say I had a point A and then B, and I wanted to find the gradient between those 2 points, A and B, then what you would have learned to do last year, or from grade 11, is to draw a line between those 2 points, and then the gradient of that straight line would be the gradient between those 2 points, okay? That was finding the average gradient. Okay. So we're going to take it a little bit further now in grade 12. Now some of you might have done this, some schools might not have looked at that average gradient concept, but basically average gradient, we were looking at finding the gradient between 2 points on a curve, and obviously you did average gradients when you looked at straight lines. You used y2 minus y1 over x2 minus x1, right? So that was finding the average gradient between 2 points. Now when we're trying to find the gradient of a curve at a single point, that's when we introduce this concept of a tangent. Remember, a tangent touches the curve at just 1 point, and we said if you want to find the gradient at a point on a curve, you need to find the gradient of the tangent at that point on the curve. Okay, but we're going to do more about tangents in next week's lesson, but I just want to touch on that concept because we are looking at finding the gradient of a curve at a single point. So if I want to find the gradient at a point A on the curve, okay, the formula we use is limit as h approaches. Remember, the arrow means approaches. So the limit as h approaches naught, and it's always naught when we're trying to find the gradient at a point, and it's of f of a plus h minus f of a all over h. So what this is saying is you have a point A, right, on a curve. So let's just draw a random curve. I've got a point here A, and then I've got another point somewhere else there, and I've moved h distance to get there. So this a plus h, don't let that confuse you. The h just means it's the distance between A and the other point. So that distance from A to A plus h will be h. Okay, so that distance, to find the gradient between those points, we say limit as h approaches naught of f of a plus h minus f of a all over h. That's your average gradient formula. When we add in the limit as h approaches naught, we are now finding the gradient at a specific point, because as h is approaching naught, it means this distance between these 2 points is getting smaller and smaller and smaller and smaller and smaller until we're just at that point A. Okay, so that's what that h approaches naught means there. So we're finding the limit at a single point. The formula we use, f of a plus h minus f of a all over h. Now some of you might already recognize this. If you've done first principles, you would recognize we would normally throw in a f dash x there in the front and say find the gradient by first principles. And then instead of an a plus h, we'd have f of x plus h minus f of x all over h. Okay, we are getting to that concept. So if you're thinking, why am I using a here? It's just because I want to show you the gradient at this point A on the curve. Okay, but we will get into this concept of finding the gradient at any points of the curve using first principles in the next slide. All right, so that's the formula we're using for now. There's no f dash x or anything. All they say is find the gradient of the curve of f of x equals x squared at the point 2, 4. So if I'm going to just use that formula, and remember I haven't introduced the concept of deriving it, so I'm just using that formula to find the gradient at a point on the curve. So it says, the formula says the limit as h approaches naught. Remember, we've got to have h approaching naught because that gives us a single point on the curve. And it's f of a plus h minus f of a all over h. And as you'll see in the next slide, we will replace the a's with x's. Okay, but in this case, I'm saying that a is this point 2. Okay, so just plugging it into the formula. F of a plus h, that means find the function value of at a plus h. So what I simply do to find f of a plus h is I substitute the a plus h in place of x in my function. So this is going to become, now look what I'm doing, the function is f of x is equal to x squared. So wherever I see a x, I'm going to put in a plus h. So this is going to become a plus h all squared. All right, I'll simplify that and I'll get a squared, or I'll FOIL it out, plus 2ah plus h squared. Okay, so that's f of a plus h. All I simply did was I used the function f of x is equal to x squared, and in place of x, I put in a plus h. Okay, hopefully you're all with me. And then to find f of a, which I need because the formula says I need to subtract f of a, I simply put that a into the formula of my function, and I get a squared. So f of a is equal to a squared. All right. Now let's put it all into the gradient formula again. So f of a plus h was that whole thing there. So it's a squared plus 2ah plus h squared minus f of a, and f of a gave me a squared, so I put that in, and then that's all over h. Okay, we simplify that, and every single time it is quite tedious and it is quite boring, but you've got to bring down this limit as h approaches naught in every single step. Okay, let's simplify. A squared minus a squared cancels, so I get 2ah plus h squared all over h. If you've done this correctly, in your second last step, you'll always end up with terms in the numerator that have h in them. The reason for that is you'll see what happens is you can pull out the h as a common factor in the numerator. So you take out the h and you'll get 2a plus h. I've just taken out a common factor in the numerator, and then that's all over h. And you see what happens is the h in the numerator and the h in the denominator will cancel. Okay, that will always happen if you've done this correctly. So we've got limits as h approaches naught of 2a plus h. All that's left to do is for me to get the answer by substituting h is equal to naught in place of that h there. So it's going to be 2a plus naught. So my answer is just going to be 2a. All right. Now that's just the general formula to find the gradient at any point on this curve. Okay, so let me go through it quickly. They said find the gradient of the curve at the point 2, 4. Now what I could have done, instead of putting this a in the formula, I could have just used 2. So I could have had f of 2 plus h minus f of 2 all over h, because they want the gradient at the point 2. So I could have done it that way, and if that's the way you saw it, then perfectly fine, you can do it that way. Alternatively, you could use the whole formula as I've done, plug it into our f of x is equal to x squared, plug in your values, and you'll get a gradient in terms of a. So we get the gradient is equal to 2a. Now remember, a in this case was the point 2, 4. Well, it was the x value of the point 2, 4. So if I want the gradient at that point 2, all I need to do is substitute x as 2 in place of a, and I'll get 2 times 2, which is 4. Okay. So you could do it this way, where you find a general term for the gradient at any point on the curve and then substitute the point you're looking for, or you could have put the point in right from the beginning. It's completely fine whichever way you choose to do it. Okay. So continuing now with this concept of finding the gradient at a point in a curve, we're going to look at deriving by first principles. Okay, now finding the derivative means you're finding the gradient of a curve at any point on the curve. That's really roughly what a derivative means. You're finding the gradient of a point on the curve when we're looking at deriving by first principles. The formula for first principles, okay, and some of you would have seen this if you've started calculus. The formula is f dash x, okay, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, and we call that the derivative of f at x. So that whole thing there, the derivative of f at x. That's what it means. Okay, so we're going to go straight into an example using that formula. The question will say, find the derivative from first principles. And guys, you have gone ahead. If they say find from first principles, you can't use any of the rules that you learn for differentiation. You have to use first principles. Okay, you'll understand what I'm talking about when I say rules when I go over the next section with you. But if they say find the derivative by first principles, you've got to use this formula. You don't have an option. All right. So I'm going to look at, I'm going to do number 2 first because I find the fractional ones are the ones that people really struggle with. And I'll leave you guys to try the first one for yourselves. F of x is equal to x squared plus x. Try that one for yourself, defining the derivative from first principles. When you do the first one, this should be your answer. And if you get that answer, then you know that you've done it correctly. Okay, so that's the answer for the first one. But I'm going to look at the fractional one because, as I say, that's fractions for some reason people battle. Okay, so the first thing we do is we write out our formula. It's the derivative of f at x is equal to, and yes, you have to keep this limit in every single step. Okay, so limit as h approaches naught of f of x plus h minus f of x all over h. Guys, you can do each of these separately. So you can find f of x plus h and then f of x and then, you know, put them all together. I'm going to do it all in one just to save us a bit of time as well. So I'm going to say limit as h approaches 0. Now for f of x plus h, it means wherever there's an x, and I'm doing question 2 here, so we find the derivative of 1 over x. So that means wherever there's an x, I need to put in x plus h. Okay, that's what f of x plus h means. So I'm going to get 1 over x plus h, because remember where there was an x, I'm putting in x plus h. All right, minus f of x. F of x is the original function, so the original function is 1 over x. And this is all over h. Okay, then that's equal to, once again, we bring down the limit as h we also, instead of saying approaches all the time, we can also say x tends to 0. So you'll often hear us interchangeably saying either x approaches or x tends to 0. It's the same thing. Okay, so I've got 1 over x plus h minus 1 over x all over h. It's a fraction. In the numerator, I need to find an LCD. And my LCD is going to be x times x plus h. So I'm going to times this fraction by x over x, and then this one by x plus h over x plus h. So my LCD is x times x plus h. All right, I'm going to times the 1 by x and then the second bit by x plus h. You'll notice that I immediately use brackets because this minus sign tells me that signs are going to change, and if I don't use the minus sign with the brackets, I'm going to mix the signs up. So important that you use the brackets. And that's all over h. All right, let's simplify a little bit further. So in the numerator, I now get x minus x, because I'm timesing the minus into the bracket. So a negative times a positive is going to give me a negative h all over x times x plus h. And what I'm going to show you here is I can also add in the h from the very bottom. I can put it here next to the whole denominator. Now the reason for that is if you've got x times x plus h in your denominator here, remember, you're going to tip and times that, so that's going to become, so it's going to look like this. I'm just going to do it on the side here. So I've got x times x plus h, and then we've got our functions here on the top, and then I'm dividing by h. All right, so that's the same as saying whatever in my numerator over x times x plus h. And then this, remember whenever you're dividing, you tip in times. So it's going to be times, this is h over 1. So if I tip it over, it's going to become times 1 over h. And so that, you see, they all just get multiplied together. So it's going to be x times x plus h times h in the denominator. So you can write it like that immediately. If you don't like to do it that way, you can do it the long way. And you can keep the h right till the end and then simplify in the end. All right, x minus x is going to give me 0, and I'm just left with negative h all over xh times x plus h. All right, and you'll see what I said to you happens before. If you've done it correctly in your second to last step or your third to last step, depending on how much you write out, in the numerator, do you see that we have no terms in x? All we have are, well, in this case, it's just 1, it's just an h, but all you'll be left with generally is terms with just h. Okay, that's important. If you don't get to just an h in that step, you've made a mistake. Okay, so this is equal to limit, just terms in h. Okay, it doesn't have to be a single h, but there's got to be terms with h in them. So what we can see is going to happen here is that h and that h is going to cancel. And we're left with minus 1 in the numerator over x times x plus h. At this point, we can tend h to 0. So in other words, we can substitute h is equal to 0 in there. And I'm simply going to be left with minus 1 over x squared. Because if this is 0, I've got x plus 0, which is just going to give me x in that bracket. And then x times x is x squared in the denominator. So I'm left with minus 1 over x squared. Okay, and that is the derivative from first principles of that function f of x is equal to 1 over x. And remember, if they say to you from first principles, you need to do it in this whole long format. Okay. I'm going to cross over to Sepo, see if there's any questions and if we need a break.
Okay, wow, mindset test. It might seem complicated when you're looking at it, but once you follow the steps, easily understandable. I hope Ufenze train Mutlonoko, you've been answered, because that's the same exact question that he had of the fraction. It's
1 over x.
Yeah, 1 over x. And the last question that I have is from Kenzo Nzwanisi. I don't know if I'm pronouncing it right, please don't kill me. He's saying, how can I find the average gradient if I am told that h approaches infinity?
How can you find the average? Okay, so now we're going into something completely different. We're going back to average gradient, and they're saying that h approaches infinity. Guys, it really will depend on the question. I mean, you obviously can't substitute infinity in. You know, like if h is approaching 0, we would substitute the 0 in. It really would depend on the kind of function you're given. Because if we were talking about a function that's undefined, you know, with asymptotes and that at certain points when h is approaching, you know, you would have to be able to see the question and judge from a specific question. So if you've got a question, send it in and I'll have a look, but you need to judge from the function. But obviously you can't substitute infinity in place of h. But say you were looking at something like this. Say you had, for example, 1 over h, and that's what you ended up with, and h was approaching. That's what I'm saying, it depends on the question. So if you ended up with the function, and after you did your average gradient and whatever, you get 1 over h. Now, if you think about this, if h is approaching infinity, okay, that means your denominator is getting really, really big. Now think, look at this. If I have 1 over 10, 1 over 100, 1 over 1,000, and then maybe 1 over 1,000,000 or something like that, these values are going to get closer and closer to 0. Okay, so what happens is, as h approaches infinity in any fraction, if this was the kind of, you know, just to give you an example of how you could use this h is approaching infinity, if h is approaching infinity, it means your denominator is getting really big. So if your denominator is getting really big, it means your fraction is getting really small. So the overall fraction would approach naught. So in this specific case, as h approaches infinity, the function will approach naught. But as I say, it really is, I think it was Kenzo or something like that. It really depends on the question. Okay, so it depends on where the h is and what your average gradient looks like, and then you can answer what would happen as h approaches infinity. But it's a case of where you'd have to judge what's happening to the overall function or fraction or whatever the case is. You obviously cannot substitute infinity in. Okay.
Awesome. Please, guys, for now, let's take this quick ad break and see you after this. Welcome back, Mindsetters. I hope you had an awesome ad break right there. Now, guys, please remember to visit our Facebook page, or simply follow us on Twitter. Simple as that. Now, Natasha, I have a question for you. They're saying determine the limit as x approaches infinity of 1 over x.
All right. Okay, so here we're looking at someone asking for the limit as x approaches infinity of 1 over x. So let's have a look at this. I briefly discussed it when I was talking about this average gradient concept just now, and we get something of 1 over h. But this is what they're asking. So the limit as x approaches infinity of 1 over x. Okay, now guys, obviously you can't substitute infinity in for anything. Infinity is infinite. We don't know what the value is, so you can't substitute it in, but you've got to think logically about what's happening here. So if we've got a fraction like 1 over x, and we're looking at the limits as x is approaching infinity, infinity is obviously really, really big. And as I was saying before, as your denominator becomes bigger and bigger, so I used the example before, 1 over 10, 1 over 100, 1 over 1,000, and you know, we could go on and on and on to 1 over a really big number. Okay, so what you're seeing is, I obviously don't know what infinity is, but I know that infinity is big, so I'm making these denominators bigger and bigger and bigger because I want to see what's going to happen to the overall function, right? So what you'll notice is these numbers get closer and closer to, and how many these would be? 1, 2, 3, 4, 5, 6. These numbers get closer and closer to 0 the bigger the denominator gets. Okay, and intuitively it makes sense because as your denominator gets bigger and bigger and bigger, your fraction gets smaller and smaller and smaller. So therefore the limit as x approaches infinity of 1 over x would be 0. Okay. If, however, and I'm just adding this in even though there's no question here, if, however, it was the limit as x approaches infinity of the function x, that's just going to get infinitely big without bound, then the answer there would be infinity. So I'm saying, alternatively, you know, just to give you guys another example, if I have the limits as x approaches infinity of the function x, if you just put big numbers in for x, x is just going to get infinitely larger and larger and larger. So therefore the limits as x approaches infinity of the function x would just be infinity. Okay, there would be no point. There wouldn't be a finite answer that you could give. Okay, so hopefully I've answered your questions on limits, and we can move on. Seppo?
Yes, we can move on, guys. Please be active on our Facebook page. I see you liking, you enjoying the show, like Pretty's enjoying the show, Yolanda's enjoying the show, and Witumelo Princess Pli is enjoying the show. Please, guys, keep on working on our page so you can continue.
All right. Okay, guys, so remember we were looking at first principles before we had that break, and we had that long formula for first principles. Now, if every time you had to find the gradient, you had to use this long formula, it would take forever. You'd never be able to finish the rest of your exam paper, so it's really not that nice. So that's why we've got this whole set of rules, which makes it really cool because it's really quick now, and we've got all these differentiation rules that help us to find the derivative really quickly. Okay, so if you learn the rules, well, you have to learn the rules because you need it for your exam, but when you learn the rules properly, you'll see that it makes life so much easier because you don't have to do the long first principles method. Okay, all right, so the rules for differentiation. The first one, the derivative of a constant is 0. So if f of x, if your function is equal to some k value and k is a constant number, then the derivative of f at x would just be equal to 0. So for example, if I had f of x is equal to 7, right, then the derivative of f at x, because the function is actually a constant number, the derivative of that would be 0. Okay. Then the power rule, if you've got a function y is equal to x to the power of n, then the derivative of y is going to be equal to n. You take that n, that power, you times it to the front of the x, or the coefficient of the x, and then you subtract 1 from the power. So if y is equal to x to the power of n, then the derivative of y is n, so I've brought the power to the front, times x to the power n minus 1, and I subtract 1 from the power. Okay? We'll go over that rule when we look at more examples. And then if we have f of x equal to k times x to the power of n, so now instead of just x to the n, you've got a coefficient here, so some number. Then all you do is it's exactly the same rule. You bring the n to the front, but you multiply it by whatever constant was already there, and then you subtract 1 from the power of x. Okay, while we're on this, I just want to show you the different ways, because you'll see I've written here f of x and I've got f dash x, and suddenly I'm using y prime. So some of the different ways to represent the derivative, the common one, f dash x. We also use y prime, or g dash x, depending on your function. Another way that you'll often see is dy over dx. Okay, and so these are just the different ways you can write derivatives. Or you might see this thing, dx, and then a bracket with a whole function in there. Okay, so those are all different notation to show that you are finding the derivative. So that's just the different notations for derivatives. Okay, now if you want to be really, really good at this section, then you need to remember all of your exponent laws. Okay, that's the only trick to being good at differentiation. You need to be really good at exponents. Okay, so if you've forgotten all of your exponents, please go back and revise that. That section is essential for this section. Okay, remember in maths everything builds up, so you need to know exponents really, really well to be able to succeed at differentiation. Okay, if they just say find the derivative of, and they give you some numbers and variables and that kind of thing, if they just say find the derivative and they give you the function values, you're just going to use the rules. Okay, the power rules and that I've showed you now. You won't do first principles. If we want you to derive by first principles, we will say find the derivative by first principles. Okay, but if you generally just asked to find the derivative of a function, you're just using the rules. Okay, I'm going to try and get through as many as possible. So let's look at the first one. We are asked to find the derivative of f of x is equal to 3x squared plus 8. All right, so we set it up, f, the derivative of f at x is equal to, now we're going to use the power rule. So the power rule says, okay, let me write it down for you again. Remember, we had if y is equal to x to the power of n, then the derivative is equal to n times x to the power n minus 1. You see what we did? We subtracted 1 from the power, and then we also brought the power to the front and multiplied by x. Okay, and if there was a coefficient, we would have multiplied by the coefficient. So here we do the same thing. we're going to bring that 2 to the front of the 3, multiply the constant by the power, so it's going to become 2 times 3. The x will stay exactly where it is, and all we do is from the power of 2, we're going to subtract 1. Okay. Then remember, now we've got a constant, an 8, and remember we said the derivative of a constant k is equal to 0. So if we're looking at a constant, any constant, the derivative of that will be 0. So therefore, I don't put anything down for the 8 because the derivative is 0. You don't have to write anything. You don't have to explain this or whatever the case is. We know that you know that the derivative is 0. So don't worry about putting anything there. Okay, so f dash x is equal to 2 times 3, which is 6, times x to the power 2 minus 1, which is just 1. Very important, please, once you've started deriving, once you've started using the rules, make sure you show that you are deriving. So you need to put your symbols in the right place. So you need to, at this point, when you've started deriving, you need to have f dash x, the derivative of f at x. You mustn't have f of x. Okay, very important, that notation. Get into the habit of using the correct notation from the beginning. Okay, so once you've started deriving, you need to put in the right notation. Okay, hopefully you guys were able to follow that and it's easy so far. We're just using the basic power rule. Okay, we're going to look at another example. This is example B. All right, and I'm going to have to just call that back up because I cannot see it. So we've got 4x cubed plus a half x squared plus x. Okay, and then this was f of x. All right. So I've got a whole lot of powers here. I'm going to use my power rule, but what you need to remember is also your rules for exponents, a half times x squared. Okay, if we had written x squared over 2, what does that mean? It means a half times x squared. Okay, so if you see a half x squared or if you see x squared over 2, the same thing. All right, so now I want to derive this. So I'm going to say f dash x. It tells the teacher that you've started deriving. Okay, once you've put that symbol in, you need to start deriving every single term. Okay, so what do? We take the 2, the power, to the front, to the coefficient, and multiply the 2 by the 4. And then we've got x to the power. From the power 2, we subtract 1. Okay, so I'm just applying the rule. And I'm going to do that for every single term. So it's going to be plus, and then again, I'm going to bring this 2 and multiply it to the half. All right, this was actually a cubed, guys. Sorry, my mistake. The question was originally a cube, and I just took it down incorrectly. So that's a 3. And that's a 3. Okay, here we've got 2, x to the power of 2, so it's going to be 2 times a half. And then x to the power of 2 minus 1 plus x to the power of, this is a 1. So again, the same thing. Take the 1, times it by the x, and it's going to be x to the power 1 minus 1. Let's simplify that. So we get 3 times 4 is 12. X to the power, 3 minus 1 is 2. Plus 2 times a half is 1. X to the power 2 minus 1 is just 1. And then I've got plus x to the power of 0. And this is why I was saying exponents become very, very important, because if you've learned your exponents, you will know that x to the power of 0 is just 1. So our answer is 12x squared plus x plus 1. All right. What you also need to remember, and you will see with the next example that we do, is when you're deriving by rule, you need to have single terms. You need to have no fractions, no brackets, no root signs or anything like that. You need to have single terms so that you can derive those terms. So before I do the last example, let's just check over with you. Do we have any questions?
Yes, we have a question from Motswabane Mimite4, and he wants to know that what's the difference between its f of x, am I saying it right? It's
F of x,
f of x and dy over dx and dx.
All right, but remember guys, when I showed you at the beginning here, when I looked at some of the different notation, f of x is a function value, so that's a function value, right? That tells you the y value on your curve, right? And then remember I showed you this notation. As soon as you start saying dx, f dash x, y dash, dy dx, you're talking about the derivative. Okay, so as soon as you start using the little dashes to show that you're finding the derivative, you're obviously finding the derivative. When there's no dash there, then you're talking about the function value. But if you also see things like dy over dx or dx of some function, you're still finding the derivative. Okay, hope that helps.
Yeah, that was a dominating question that they had.
Okay.
So, and another question is a fraction question. It's quite hectic for the guys at home. So I hope the next question still has a fraction and you can see what she will be doing. So for now, you can still continue.
All right, guys. So yeah, the next question does have a fraction in it and it has roots. So it's got fractions and roots, things that people hate for some reason. I don't know why. I don't think we're going to have time to do D and E. So I'm just going to keep it on the screen. And if you guys can please take it down and try and do that by yourself. Okay, I'm going to look at C. All right, so D is y is equal to minus x squared times x minus 2. And then E is y is equal to x squared minus 2x plus 2 all over x. Just remember that when you derive, you have to get rid of all brackets and you need to get rid of all your fractional values where x is in the denominator. If it's just something over 2 or 3 or 4, whatever, it's fine. But if there's an x in the denominator, you need to get it out of the denominator using exponents. Okay, so this is a nice one. F of x is equal to the square root of x plus 1 over the square root of x. And this is question C. We're going to go through it quite quickly. So we've got f of x is equal to the square root of x plus 1 over the square root of x. Guys, it becomes very, very important here to do exponents, right? I'm not doing any deriving yet. If I want to take x out of the root sign from exponents, remember, it's going to be, so if I have some m here, some n here, to take it out, it's always the inside divided by the outside. So the mth root of x to the power n is x to the m over n. This is exponents. All right? So the root of x I can rewrite as x to the power of a half plus 1 over the square root of x is 1 over x to the power of a half. We cannot have fractions if we want to derive with x in the denominator. So I take this to the numerator and it becomes x to the power minus a half. Okay, now you see I've gotten rid of my fractionals and my roots and that. Now I derive. It's going to be a half times x to the power 1 minus a half x to the power minus a half minus 1. All right, we're going to quickly try and finish this. I know that we've got it's like 1 second. So it's going to be x to the power of minus a half times x to the power minus 3 over 2.
Guys,
okay,
time
guys,
is not
we
on our
had to
side.
quickly go finish that Sepo.
Yes.
Unfortunately, I couldn't leave that one just hanging.
Guys, see you next time, same place, next week, different topic. Love you. Out of here.